Good morning. Um, so today I want to talk about what's called analytic edit spaces. Um, right. But I want to immediately point out that there is some conflict of notation here, or conflict of terminology. Um, so basically, using what we've said so far, all edit spaces give rise to analytic spaces in our sense, and spaces of state or whatever they will be in our sense. Uh, but within the world of edit spaces, there was already a qualifier called analytic. Um, but within the theory of edit spaces. There are called analytic ones.
What is this? Conflict of terminology.
Yeah. Um, uh, and I didn't come up with a good name for them. But there's one name that's already to some extent used in this world of edit spaces also. So I will call them Tate in this lecture.
Peter, it would help us if you could write a bit bigger, because it's just a bit unclear.
There is a shadow or something.
Yeah.
Also.
Okay. Yeah. Yeah, just that I don't want to overuse the word analytic in this. Okay, so here's the definition where this is already used this name. So a Hoover A is called fake. So this is terminology that's already in use. If it has a topological uniform unit. Such a thing is also called a pseudo uniform. Right, so the example to keep in mind is, for example, TP, where P is a topological unipotent unit, or in fact any non-Euclidean local field. Complete, of course, we are always seeing completeness. Or any kind of Banach algebra there over, or any Huber ring over. Because when you have a topology unipotent unit in some ring, then for anything above, you also. And then we call it an space state. So that's usually called analytic. If it is covered. So we didn't really discuss the full definition of edit spaces, but we discussed the algebras that give rise to them, and then there's some way of doing them, which will not be all that important for us right now. And basically, we told you what the open subsets are, and then you kind of do the obvious thing. We discovered quite such a plus with HA. It's actually equivalent to a pointwise condition that
Here I speak, in the green I speak.
Green speak.
So just to clarify, first, you did not define analytic spaces in our sense because
I did not define yes yet.
And yeah, okay. And also adic spaces, there was classically there is a subtlety about shiftiness. So there is this condition in Uber that, and then it seems
if I say adic space right now, I probably mean Shifi. Okay.
Yeah, but then there is also the question of whether in this theory of localization that Dustin talked about last time, when you do this, you get some condensed thing, possibly. You get some condensed thing for an affinoid for a rational domain, and it is
over.
What did you say? You will come to this?
I will come to it, okay?
Okay. So you need some, in all cases of interest, I mean, usually it gives the right thing, but it's, I don't know if for any shifty thing it gives, I'm not sure.
Over, I will come to it. So if you have any space, you can actually at each point on X, you can define a so-called completed residue field. And these can either be just discrete rings or they can be complete non-Archimedean fields. And you're somehow asking that there are no points where it is a discrete ring. Not okay, and so then, yeah, basically the series set up so that the residue fields are always of either of these forms. But then when you have such a complete non-Archimedean field, then there is some topological equivalent unit in there, and you can somehow lift this to a small neighborhood, and that's why locally there's such a thing. And so the intuition is that there's a world of schemes. This fits in some world of formal schemes. And maybe with some adjectives that I don't want to discuss right now because it's not really relevant. These all fit within Huber's theory of adic spaces. But then these are some of things where you start with a scheme and there is still some kind of large space where it's scheme-like, or at least like the underlying reduced. But then these analytic adic space areas are some of the ones, morally speaking, where you start with a formal scheme, but then remove all the scheme-like points. So you state adic spaces, which are at the other end. Okay. And so, I mean, here you might have something like F, like F. Then here you have something like split VP, which you can also consider as some kind of spa VP VP, adic space. But then the generic fiber is such an state that makes sense. Okay, let me say a few words about the structure of such Huber rings. So let's say, right. So we always have these rings of definitions. So, okay, so let's say pi in A such a topologically important unit, so studio implementer. Then you can take such a ring of definitions And you can always assume that they contain any given power bonded element, and I mean it's topology nilpotent, in particular power bonded. So you can, without loss of general, assume that your previous definition contains pi. You could also do it in such a way that you can take any and then some power of pi will anyways live in there. Any power of pi is still the unit. And then actually it's automatically the case that A0 carries the pi at topology. That's a nice little exercise in looking at the axioms of the topology on a Burr. So a priori, you might think that it could have some rather more subtle I-adic topology for the finitely generated ideal I, but actually it's always just generated by this pi. And then you can actually turn A into a Banach algebra. With unit for A0. So, for example, you could say that the norm of any function f is 2 to the minus n, where n is a maximum for all integers m, such that pi to the m is technically contains the primo because it could also be inserted. And so in particular, this means that the norm of pi, if I set it up right, pi to the minus n, the norm of pi should be a half, and the norm of pi inverse should be 2. And of course, there's some kind of arbitrary choice that I made here. Both first of them is sort of uniformize a pi and in like the number a half here.
There is a trivial counterexample with the zero ring. So the norm of pi would be 0, I think, there.
Is the zero ring Tate? I don't think it has a topology important unit, right? Oh, it doesn't, I mean, maybe that's a counterexample to my claim that anything that is an algebra over Tate ring is a benefit.
No, but zero is supposed to be equal to unit. Zero is supposed to be equal to unit in the zero ring.
Zero is a topology. Okay. Probably. Okay, so whatever. You figure it out what comes through there. And so there's actually Nixon equivalence. Between state rings. And Banach algebras or Banach rings admitting, and so maybe I should say something for independent ring. First of all, I say what the objects are. The objects are Banach rings admitting some Banach rings admitting some pi in B such that the norm of pi is strictly between 0 and 1, and the norm of pi times the norm of pi inverse is equal to 1. But as a moment, you actually only care about the topology induced by the Banach norm. So and again, before somebody complains, everything here is completed. Banach rings and continuous nets.
So you mean ultrametric Banach rings? Otherwise, you have, and of course, the zero is still a counterexample to.
Yeah, what happens to zero, I think. And continuous. Um, um, right. Okay, so these are like basic algebras that we consider here. So you could also talk about these somewhat in the language of Banach algebras, but you shouldn't really fix a norm, but you should just ask it to defined by some norm this property that we have. That's pseudo infinited. All right, so then let me already come to so now I want to state a theorem that Kedlai and Liu proved when some 10 years ago or so, and a theorem that I found extremely striking and surprising at the time. So as was discussed, there are all these issues that for a general Huber ring or Huber pair, what Huber defines is not always actually a sheaf. So let's just say that the pair A plus is sheafy. If what Huber defines a pre-sheaf of Huber rings if this is a sheaf. Yeah, it's some kind of stupid definition. And I did certainly expect that in those cases where you can prove that something is sheafy, you can probably also prove other nice properties, because then that's probably the reason that things are well behaved. What I did not at all expect is that you could prove any non-trivial theorem whose only hypothesis is something is sheafy and then other good things happen. Because if I'm only asking for there's the first thing that could break, that this is not a sheaf, but they expect that if you're in a situation where, there might be situations where just for stupid reason this is a sheaf, and then why should other good things? That's okay. But Kedlai and Liu proved the following striking theorem. So assume A is fixed, and A plus is keeping. Then any finite projective module over A, you can take it and tensor it over, tensor it with over A, which was structure sheaf. And A is just a direct summit over 3 A modules. So certainly this is still a sheaf. That's good. So it's a sheaf of finite projective modules. Actually, it's one that's locally free. So there's a locally free of finite ring. And so whenever you have ring space, you can always talk about these modules which are locally free of finite ring. So these are, I guess, usually called the vector bundles. vector bundle points by with respect to Hubert. And okay, so it's easy to see that this is a fully faithful functor, but the highly non-trivial and surprising fact is that it's actually an equivalence. So that whenever you can glue vector bundle. Oh, one can glue finite protective module. And somewhat later, they also proved that there is some version of this that works for some kind of coherent or pseudo-coherent modules, but I don't want to state the precise theorem because the precise result is actually a bit subtle. For vector bundle, it's extremely clean. Let me just say there is a version for so-called pseudo-coherent. Then at least if the ring is Noetherian, it recovers the expected result that you can glue coherent. Well, even if the rings are missing, you have to be a bit careful with the combination. Because localization actually might not be clear. But yes. All right, so this is a really nice result. It's like basically maybe that their aim at the time was just to prove that on perfectoid spaces you can do vector bundles, but the argument somehow worked actually whenever it just it's sheafy. And I mean I could kind of follow their argument line by line, but it's some kind of rather tricky argument where you really have to. I mean, when you have a descent datum for a vector bundle, somehow it's more or less some kind of irreversible matrix over some completion of your ring, and then you have to do some changes of bases to make things better. And it's actually it's an actual analysis somehow. And so today I want to explain different proofs that we can give using our general theory of let's call it modes. I mean, using the right. That's similarly this way also. I should maybe say that back some 10 years ago, when Belay and Lear proved this result, I was also talking to Kobe Tremnitzer, and he was somehow already telling me that actually, like if you work in the derived category and you look at some kind of in-Banach modules, then you can just glue. And I was like, okay, but what does it even mean? Like we have all these problems. Our thing is not a structure sheaf, and it's like it seems highly non-trivial to do vector bounds and so on. So what does this extremely general descent result actually tell you about such concrete questions? And I don't know whether he ever like figured that out, but somehow the goal of this lecture is somehow to show that this is not just some fancy. I mean, this descent result for these solid modules was kind of, I don't know, abstract, and maybe didn't see much happening. And so I want to show how you can actually get down to something more concrete today. Okay, so they're basically right. Okay, so the outlines. So first of all, and this is somehow addressing what Gabor already wants to know, is the relation between the thing that Hubert defined and this structure key from last time. So some of the thing that naturally comes out of our theory. In particular, we will actually, it's actually true that if it so happens that this thing is achieved, then it actually happens to agree always with our structure sheet, which is why suddenly the good things happen, because then it actually has the correct theory. We already find the correct theory. And the second thing is that, well, in general, sending any rational subset U to let's say with two coherent modules in non-negative homological degrees over Q, where this is now the thing that's in general derived. So there's a full subcategory of C. This is a sheet of thing. So you cannot just glue within this huge category, but also like more reasonable objects, they also glue to reasonable objects. And then once you, like in the most general case, that's the best thing you can hope for. It addresses like the subtleties in the precise formulation of this result for two coherent modules. But once you restrict to vector bundles, you can then prove this very clean result. And maybe I should also say that the reference with this done in more detail is this paper of 3D orientation. Okay, so the first thing, some of the relations. So let me call the other thing just um, right. So first of all, here's the proposition. That somehow just computes both sides. Let's say you have such a rational open subset. So I should say from do I need it here? In my mind, I'm making the blanket assumption that A is state from throughout this lecture. It may or may not be necessary for everything I'm saying. Okay, so this will be a rational subset. So here I'm really using this Edding spectrum of continuous valuations, which concretely means that when I form such a rational subset, I should assume that the ideal generated by F1 through N A is an open ideal, but actually once you have a topological Liebman unit, it must be equal to A. Then first of all, Huber's structure is given by taking the convergent power series algebra and variables G1 to Gn, and then modding out by the ideal generates like GC1 minus F1, the GCN minus F1, and taking the closure. I this is basically yeah. So why is that? So somehow on this open subset. Well, first of all, you did invert G because now the ideal generated by G contains F1 up to Fn, but they generate the unit ideal. So the ideal generated by G must be the unit ideal. So G has become invertible, even without taking the closure. And then on this, also, so you have now an element T1, which is F1 over G, and all its convergent power series. So some of you kind of, and this is what should happen on the subset where this is equal to this. But I mean, Huber, he was always working with complete topological rings. So when you take a quotient by something, you also take the quotient by the closure. And then, well, for example, but I mean, this is a Banach algebra, and the quotient by any closed ideal is still a Banach algebra. And it's still a Huber ring, H Huber ring. Okay, so this is maybe not so hard to show. And all of you, which I recall the endomorphisms, or is the image of A and well, I mean, it's a thing that's just been defined last time, yeah. You take you define a category analytic ring structure by asking for this completeness for all these elements of 1 over D, and then you somehow look at what the completion of the unit actually is, and this is what this overview is. And this has a very similar formula. Okay, you want to Tn, but then take the derived quotient. Where here for condensed ring R and elements x1 through n and R. This derived quotient signifies the derived base change from polynomial algebra. Like they just modeled by all the variables xi. So basically, you're setting xi also to 0, but not just in the stupid way, but in the derived way. And concretely, this is computed by Kosovo complex. And in the middle, there are some white eyes. But, this is Kosovo differentials. And it's just by taking the standard resolution of Z over here.
Can you say in which case you get a solution?
It will be an animated condensed ring, and that's why I will consider this. I don't really want to talk about animated things today, but yeah, so. Just, yeah, so it's certainly some kind of commutative algebra in the derived category. Let me just give a sketch. And for the second part, so you can write A1 over D as A joins D1 here. Mod. And now it's not really necessary whether I take the drive quotient or not, but it's also true in the drive sense because what I will break down is a regular sequence. Um, and then you solidify uh, solidify this. So this is somehow an exact operation in the rough category. So like, this thing is just computed by a Kossel complex, which just contains a finite complex with finite direct sums of the complex of this ring. So somehow to understand what this Kossel thing just passes through the solidification. So you just have to understand what happens when you solidify these things. But this is exactly what Dustin already computed, that this somehow turns. I mean, he had to say that if you take a ring, or take the function that takes a module, and then joins a new variable t, and then solidifies for this variable, this computes with all limits and co-limits. And so somehow then you can write A. First of all, it's A0, ring of definition, invert pi, but then A0 is the limit of A0 mod pi to the n's. So this way you can, like this operation of joining these variables and then solidifying jointly, and commutes with this description of A as a limit, co-limit of limits. And so. Okay, and so a corollary is actually that Hoover's thing, let's say mu, is the same thing as taking R over V, which is a complex, but by zero of it is just the usual condensed string. And then you take the quantum separated quotient. So here's a small interlude. The inclusion from light or not, it doesn't really matter. Quasi separated condensed set inside of all condensed sets. It has a left adjoint. I'll take any x to the quasi separated quotient, and it is mimicking the operation of taking the maximal Hausdorff quotient. And like in practice, that's precisely what it does. One very nice feature that this left adjoint has for non-obvious reasons is actually the commutes with finite products. It does not in general commute with finite limits, but it does commute with finite products. This has a good effect that if X has some kind of algebraic structure, like being a group or a ring and so on, then the quasi-separated function of that is algebraic structure.
Is the preservation of finite product is available both for the light setting and all condensates?
Yes, it's true in the lighting. I mean, also if you start with the light condensed, and then from the maximal quasi-separated quotient is also light and so on. So.
Thank you.
Right. So concretely, if you write X as a quotient of some X divided by R, where it's telling you how to compute this, that's the left adjoint. I mean, you can always write any condensed set as a quotient of a quasi-separator. Just take a disjoint unit of profinite sets projecting onto it. By some equivalency. Then there exists a minimal quasi-compact injection R bar in R that is also equivalent in the equivalent relation. And containing R. So it's in some sense taking the closure of R, intuitively speaking. But sometimes it adds new things where the equivalence relation is not spreading. So you add that as well, and then you do some kind of transition induction. Or you just intersect all possible quasi-complex injections that are equivalence relation and contains this, and the intersection is still an equivalent relation. And so then X is this X. And so the quasi-separated quotient is this X modulo. Because I mean, this X was quasi-separated to start with, if and only if this inclusion here of this equivalence relation was quasi-complex. And so, for example, yeah. So if X happens to be a group, then you can always also find a projection from a quasi-separated condensed to be a group, and then the equivalence relation is just the quotient by a subgroup. In that case, you're really just taking the quotient by the closure of the subgroup. The closure in the sense of smallest quasi-compact injection. Okay, and so here's one other thing I should recall, which is what do quasi-compact injections have to do with closures, as I was pretending to have. Let's say X is any sequential space. To recall that sequential topological spaces were those for which the map to condensed sets is fully faithful. Then the closed subsets of X map bijectively to the to the quasi-compact injections. Interest. Taking any taking an EZ here. Actually, no. So for example, why, if you start with a closed subset here, why is it actually quasi-compact injection? Well, to check that, the definition is that whenever you pull back to some profinite set, then the pre-image, this is a quasi-compact injection, but this precisely means that the other guy is also, yeah. I mean, so the pre-image in this case is just the closed subset of this profinite set, like starting the closed subset here. And yeah, so the closed subset of the profinite set is itself a profinite set, and hence quasi-compact. Using that X has some of this quotient topology from profinite sets, you can kind of also reverse it, reason it. Okay. And so okay, so back to the corollary. Well, what is phi zero for view? Well, this is just the thing, and then you just take the actual constant. Like and then if you take a product separated quotient, well, this guy is already product separated. And then by this recipe above, and because this here is actually a sequential, comes from a sequential topological space, this precisely means that I should just replace this one here by its closure. Which is what's it? Right. And so this already gives us some relation, but we are interested in a somewhat more precise relation, which is the following theorem that's essentially due to Gedalia. Except that he didn't use this language to phrase it, but I mean, the proof is really his. That A plus GT, if and only if Hoover structure is constant. Or if it's just phrased in terms of all series, so for all view rational, all view fits in degree 0. And it's about separated. Okay, so let me give the proof. This is clear because by the general descent results from the last lecture, we have this sheaf of categories, but in particular, like we get a sheaf of rings if we just take the involving those unit, and this is O. And so this is a sheaf, and then, well, this is a sheaf. The non-trivial and I think somewhat surprising result is that if it so happens to be sheafy, then actually it is the right thing. But you get the other direction. And before I start, note that to check this property that all of U sits in degree 0 and is Pauli separated, it suffices to show that this is true on a further refinement of U, further cover of U, because you can always recover it by all the smaller values as a limit. And then, as Dustin used it last time, there are these arguments that general rational covers and so on, they can always be refined by these simple Laurent covers. And actually, the second type of cover that he uses is actually not necessary in this state setting. So right, so the stuff is to check the good property of all of U after a further refinement. And I don't want to go through all those combinatorics of how it does these refinements, and just note that it's somewhat reduced to the following T lambda. Yes. Also, can always refine that. We can always cover any space with a locus where f is at most one and at least one. And so the other type of cover is not necessary when you're topologically nilpotent unit. And so this reduces to the following assertion. So let's say we take it. And f among the names. And assume that this sequence is exact. Actually, what does sheafiness mean? Sheafiness, so I mean, so this is O of X. or Hoover. Well, actually, this the most local squares, the most one. Or Hoover, the local squares. So let me omit to 0 here. There's a local where they're equal. And this is just what the sheaf condition says, right? So if you want to give a thing here, you have to give one here, and this open cover, and they need to agree on this intersection. It's actually always true that the last map is surjective, just because any element in here can be written as kind of a sum of f to the n's and 1 over f to the n's, and the f to the n's come from here, and 1 over f to the n's come from here. So actually, surjectivity on the right is always true. Never mind that. So assume this, which is always true of a sheaf, because it's just one specific instance of the sheaf axiom. Then actually, this is the derived quotient by the T minus f, and the other thing is also the derived quotient by 1 minus. So in other words, it agrees with the thing that we define. Or, I mean, also, what does this derived quotient mean? It means that multiplication by T minus f is actually injective here, and it has closing. Right, so let's prove this. So what do you have to see? What I just said, so that if you look at A joint T, and then multiply by, let's say, T minus f, or also by 1 minus T times f, and go to A joint T, that this is injective with closed limit. Sure. But actually, because of star, like for example, if you want to show injectivity, let's assume you have something in the kernel that also still lies in the kernel when you replace A by one of those two rings. But then over those two rings, I will argue that it's easy to see that this map actually is injective. But then this map here we assume to be injective, and so we get the injectivity. And similarly, this map actually has closed image because the image is precisely the kernel of the next map. And so using this, you can also check that if it's over these rings it has closed image, then also here it must have closed image. So it's enough to take it over those the assertion of once we replace A by those two rings. In other words, we can assume that either the absolute value of S is less or equal to 1, or one of these solved, not highlighted. But when, for example, f is less than or equal to 1, then t minus f, you can actually easily show that it's a closed ideal because you can just successively like kill off the highest coefficient. And it's something similar here. So yeah, in those two cases, it's actually something new. And you can really just, yeah, I mean, if you have an element here, you can really just by looking at coefficients kind of see what happens. And also, like, I mean, once it hits a base change, actually one of them becomes a tautology anyways, because you're like not doing any further localization, and then it's only the other one you have to check. But yeah, some damage. Basically, if say f has absolute value close to 1, then the second thing is the one where you ask that f has also absolute value greater or equal to 1. But this basically just means that you invert f the ring of integral elements, and so already on the level of A0, it becomes the localization, and then things are good. Okay, so this is this funny argument that Kedaya found that if you just assume that Hoover's thing is a sheaf, then you can, yeah, reduce this problem. And it's somehow critical that you can reduce to the simple Laurent covers where you just take a quotient by one element, because then the question, what this derived quotient is really just a question whether this one map here is injective with closed image. Yeah, this can be reduced. Okay, so this finishes my discussion about the sheafiness condition and the relation between Hoover's structure sheaf and our structure sheaf. And so now come to the second part, which is the gluing of like pseudo or complex. So here the definitions. What does the pseudo mean? So let R be any ring. This Greek say. No condensed structure for now. Then some complex C in the Dirac categories. Pseudo this definition is SGH6, I believe. If it can be represented by a complex so it goes up to some C minus n, but then it goes to 0. But then can go arbitrarily far to the left. Yeah, so there is some stop here, it goes only to the left. And all of these terms must be finite state. Yeah, and you could also say that finite projective wouldn't make a difference. Finite free. Let me actually say finite projective because I want to say something else in a second, and then important. So if your ring was Noetherian, then this would just be the, or more generally coherent, this would just be the condition that each it's bounded to the right, and each homology group is a coherent module. In the Noetherian case, just a finitely generated module. But you can go arbitrarily far to the left. If you're not on a Noetherian ring, then there's some coherent modules don't form in a being category usually, and so because you somehow didn't ask that the relations between the relations are also finitely generated, and so some of these infinite complexes, they capture the idea that you have modules which are finitely generated with finitely many relations, with finitely many further relations, and so on. So, like, I guess the point is that over in the Noetherian ring, there is a good class of like finitely generated modules that behaving nicely. You don't have that over a general ring, but over a general ring, you still have in the right category this nice class of pretty coherent complexes. And let me not call that C is perfect. If there is such a representation which is bounded to the left. Then bounded. It's just a finite complex of finite projective modules. And then the theorem is that, let's say AA plus is any Huber pair it's in the A state. Then setting any Q by the star A plus rational subset to the following things. So on the one hand, you can take pseudo-coherent guys, all the ones, or you can take pseudo-coherent ones that are, let's say, in degrees greater or equal to 0, or greater or equal to n for any n. You could also take all perfect complexes, but you could also take those perfect complexes which have such a representation in some interval. So this perf AD means those that can be represented using a complex sitting in those degrees. So these are all functors that take a rational subset to infinity category, and they all free sheaves certainly, and the claim that they are all sheaves of this. On the right, I'm always just thinking of A as a satisfy that I really just mean the underlying things. So these are modules similar without topology. Of course, being somewhat pseudo-coherent is not why a unique reason of topology.
Peter, you didn't have a dependence on U on the right-hand side.
I did not, thank you. And I guess implicitly I'm now extending all these notions to animated rings. And so, okay, so either you know what all these things mean when this guy is just an animated ring, and then it's true as stated, or you're secretly assume that you maybe in the Sheafly case where there's just constant degree 0, and then I just told you what they are. Either way, these are sheets of the same case. In particular, the case first 0, 0, these are exactly the vector bundles this recovers theorem of similarities.
Peter, is there a reason you didn't state the like pseudo-coherent AB?
Uh, 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 no,
Okay.
just means something slightly different. I could also say that one. Yeah. And you have to be slightly careful that the good way to make amplitude restrictions on coherent sheaves and on perfect complex are different. Yeah. For perfect complexes, you should assume that there is a representation as an actual complex that's in some bounded range of degrees. For coherent sheaves, you can just make them more a naive thing like bounds the degrees in which it fits. Although no, there is actually a reason. There is a reason. Because I don't think localizations are flat in any generality here. So you could have something that's in degree 0 that when you localize goes further to the left.
Won't they be flat? I mean, on the level of the discrete rings? Maybe not always.
Oh, no. I mean, it's still, I think, an open question whether for perfectoid spaces the localization is set to be flat.
Oh, okay.
I think everybody expects it's wrong, but I don't think anybody is actually. Okay. So I guess I only have half an hour remaining, so let me just give an overview of the argument. So, I mean, as I said, this is in this paper of Gregory and Dolchak. And we also gave we proved the analog of this result in our causal complex geometry. And the same argument as there works here. But okay, let me recall the arguments. So we know that this function that takes any u to like the f of u or v plus call it. And okay, this will have a meaning at some point when this is animated. Sometimes we didn't discuss it yet, so if you feel more comfortable, just assume that this sits in degree 0. And the sheaf case. Then this is a sheaf of any categories. And so this certainly contains fully faithfully just the modules over the underlying discrete ring. That's always true. For any analytic ring whatsoever. And this certainly contains all these other subcategories. Which are basically some kind of, yeah, this is some kind of finite disposition here. And so by virtue of this being fully faithful, you already, it means that the only thing actually you have to prove in all these settings is that if you have an object in here, which locally happens to lie in all of these subcategories and actually lies so globally. And maybe at the expense of pretending that I can replace all of u by a again. The assertion that if this is such that over a cover, like the base change from a plus call it lies in one of these subcategories. then so does. So the conditions that we put, they glue. Okay. And so maybe the first idea you might have is that, well, let's first check that this condition of being like a module, a discrete module descends, and then use the sense fibrous conditions. But this actually does not work. So the warning, and this is a warning that Dustin already made, but I want to reiterate it because it's important. The condition analyzes the gross category of the underlying discrete ring. Does I'm making this noise? Sorry. This does not just let's say globalized. But if it's too locally, that need not be too globally. Let me actually quickly sketch one example. I'm not sure it's the easiest example, but somewhat destructive. Let's consider take elliptic curve. So it takes a GM as an Edding space over, I don't know, let's say QP. And then you can take the quotient by, let's say, p to the v, or some other topology equivalent unit. So this is what's called a take elliptic curve. So it's the analog of taking C star, complex elliptic space C star, and quotient by some topology equivalent element, and then this becomes a elliptic curve of the complex numbers, and you do a similar thing over an Archimedes field. So that's somehow how rigid geometry started. And let's assume that our SPA A plus is some large open subset here. So basically, remove a small disk around the one or something like this. But large enough that you somehow see that there is this non-trivial global monodromy. But it shouldn't split back. It should really be a subset only of the quotient and not lift to GM. And then there is certainly the projection that, yeah, right? Five was sometimes in the pseudo device. G was sometimes in my ring. And then you can define what I will call a lower streak of the structure treatment here. What is this? Well, locally this map is just split, and so locally on the base, like the fiber glitches are just discount union of copies of the base indexed by the integers, and then the sheaf is just a direct sum of copies of this thing. And so this is how it's defined locally, and well, it's obviously a sheaf, and so it glues to some sheaf on the base. So this defines for you an object in DAA plus solid, because locally it does. Okay. And it is locally discrete, because locally, as I said, this coverage just splits, and this is just a bunch of copies of your base ring, infinite dimensions. But you can check that globally it isn't discrete, and exercise. Okay, so we can't hope to use this category, and instead we will use two other notions. So instead, you can first also define this kind of pseudo-coherent notion. Where now, I mean, yeah, it's again the complexes which are represented by something that's bounded to the right, so goes to the left. And OCI are, in this case, I can just say they are equal to these. All right, or more generally, like projective models. I guess implicitly when I say it like this, I assume that P is also still degree 0. In general, you should do the appropriate thing where it makes this right. There's a different way to characterize this as X out of the sky computing with filtered polymers.
You meant mod AA plus solid.
Yes, thanks. It's the right. So you define this and show that the property of lying there globalized. And for this, you actually just use, I mean, first of all, being bounded to the right is a property that globalizes because you're locally bounded to the right, and then globally you're just some kind of finite limit of such, and so you're still bounded to the right. And so then you need to check this X condition. And to check that, the only thing you need is that these localizations have bounded to amplitude. Otherwise, there would be an issue with some boundedness issue, but given that the localizations are bounded to the left, this is fine. Using that localizations. Okay, so this finiteness condition on the big category, this can be decided. And then actually, once you have the finiteness condition, then the discreteness is also something that can be just globalized. But this is actually not immediately how you prove it and somehow equivalent to what you want to prove. So the issue there up there is really that it's infinite. And so to do the argument, we actually isolated this second subclass of nice objects in this A plus solid, and these are the so-called nuclear objects. The objects of nuclear ones. So maybe we will discuss them much more generally, in much more detail later. Let me just give a quick definition here. So all the discrete ones will be modular, but the nuclear things are somewhat more general than that. So in particular, they contain all Banach modules, but not the Smith ones. So let's say C. Right. Smooth pair. So by the way, the name is inspired by this class of nuclear vector space that Grothendieck defined in functional analysis. It's not a completely precise translation, but like in spirit, it is one. If the following condition is satisfied, so you take the internal home for P. So P, as usual, is my, maybe I should have said before. I mean, this is my usual P module on the most. So you have that. On the other hand, one way to produce maps is to start with a dual of P, and then tensor C. And these are in some sense a kind of trace class maps. So this is in some way encoding the idea that all maps from P are trace class. So a couple of comments about the definition. So in general, the nuclear, so actually in this case, the nuclear modules they are generated in the colimits and shifts. By just a Banach module, like, I don't know, the zero function from N to A. So if you want, it's also A joint P, but just as a module. So in general, you can generate them by colimits. sequential colimits, in general, referring to more general analytic rings, where these are all trace class matrices. Meaning they come from elements in Qi dual tensor like this. Whenever you have an element in the tensor product, you can produce a map from Qi to Qi plus 1. These are the maps we call trace class. And then if you take a sequential colimit of such trace class maps, you can check using that as internal home commuters colimits that will always have this property. And conversely, when you try to start presenting a nuclear object in terms of how it's generated by compact projectors, and somehow take a finite complex of compact projectors mapping into C. But then that map will actually will be trace class, and you can factor it over like trace class map, and this is how this is right. Okay, and so yeah, in particular, like over QP, this is stuff generated by Bonn QP vector spaces. Okay. So there's still a rather large class of guys. It will actually, I mean, there's actually this theory of Sasha Efimov about K-series of dualizable categories and so on. One very nice property is this nuclear module sets that they can form a dualizable category. The universal dualizable approximation in some sense to the right hand side. Using this, you can also define the K-series of Edding spaces, which is an Andrei-Shev list, but this is not taking us the field. So back to here. So you have the subclass of nuclear guys, and so you define this class, and then you show that this property with global values. And so you want to check that if you have some C and it satisfies this condition locally, then you want to check it globally. And for this, certainly the ideal situation is that just that those sides of this isomorphism can just localize. Well, the right-hand side is just some tensoring, so the right-hand side definitely like localizes. The question is whether the left-hand side also does, and it actually does. And so the key thing is that P is that the internal home from P commutes with localization. But there's the same argument that Dustin used last time, which showed that different localizations commute with each other, because he actually showed that all the localizations are given by internal home from some object. And so different internal homes can meet with each other. Okay, so
I mean, Peter, I mean, strictly speaking, that's not I mean, for like an algebraic localization, inverting an element, you know, it's not literally internal home from some object.
Take Edding spaces, and they're all rational subsets. Like inverting an element is not a rational subset. So for a general Edding space, I should say with a suitably large class of localizations, but
yeah. I mean, and in any case, you can always refine further so that it is. Yeah, I just wanted to, just in case there was some confusion about that.
Well, actually, also, right. I mean, well, I think also commute with the other type of localizations, because this also commutes with inverting an element, because it commutes with colimits, but okay. Right. And so now we've isolated two classes, these things that are pseudo-coherent in the sense of the big category, and these nuclear guys.
So excuse me. So consider this question of commutative localization. It seems that the sketchy argument you gave doesn't use that you put there P. You can put anything, not necessarily compact, instead of P. Is it right? And this commutative localization, which is contrary to what we have for schemes, where you have to take underlying Rho from something.
It's a bit surprising. Yeah. So actually, in this case, also localizations, they commute with all products because they have a left adjoint, which is something we'll discuss, and which is extremely important for this whole theory of complex sport coherent cohomology. That actually, in these situations, the pullback functor, there's a kind of coherent lower Schritt functor, which is, yeah, it's the left adjoint, so the pullback commutes all limits, but it's also satisfies the projection formula with lower Schritt. And this is precisely equivalent to this internal.
So it is true for anything instead of P.
It's true for anything instead of P. This
okay.
property. For these variants that Dustin mentioned, it's however again important that this internal convolution for the columns. But for the precise localization we're interested in here to rational open subsets, it's actually always true. Right, and I should wrap up. And so then, okay, so we have made two steps in our proof. We isolated two different classes of modules that can be glued. And then the last step is to isolate, so then also intersection. And then the last step is to show that pseudo-coherent guys over separate, it's just an inclusion. So they are certainly pseudo-coherent in the sense of the split category. And they are also nucleus. But this is actually called. And so then he finally showed that you can do these pseudo-coherent ones. Then there's still a little bit to show that all the other super and subscripts I put also glue, but this is actually easy. And so, right, I mean, so far, I didn't do anything that seemed remotely like analysis. But someone who's doing a vector bundle, there is actually some maneuvers with power series that you have to undertake somewhere. So somewhere there has to be some actual work, right? And so it's somehow in this step. And let me actually show how it's done. So CMC is in this intersection. And so we can assume we have some complex, and by shifting, we can assume it starts at 0. And I also said we can assume that these are all just P. Okay. We have such a complex, and we know that it is nuclear. Right? But now I certainly have a map from P to here, which is just the identity here, and my complex is just 0 elsewhere. Right? There's a map of complexes. This is a map from P into C, right? Now, being nuclear, it means that it's trace class. And so if you actually have a section in here, then again, you can factor this over some approximation to C. And so when you think a little bit about what this means, then you realize that you can actually there exists a diagram like this, where G says where G is trace class. But then this here is actually surjective, so this F can actually be split back and and so you get actually some endomorphism here. And actually what you see with this is that the map from B to C factors over the mapping cone 1 minus G to P for some trace cloud endomorphism D of P. So this is just some playing around with the fact that P is projective and so on, and the definition of nuclearity, reduced trace cloud things and so on. So yeah. Right, so in the end, you see that there is actually a way to put 1 minus P here. And then. And so then it's actually enough to show that this guy here it's to the period that it's actually lies, it's actually a perfect concept. And certainly this representation as I've written it doesn't show that. But they claim that as far as I'm to a complex that these are just finite free modules here. And this is basically a classical Freighton theory. So if you have a trace cloud operator, so the identity map is certainly a Freighton operator, and then you perturb this by a trace cloud, in particular a compact operator. And then any perturbation of a Freighton operator by a compact operator is still Freighton. And Freighton operators somehow have the properties that are kernel and co-kernel are finite dimensional. And this is the argument that you just have to execute slightly more carefully in the situation. So this is some Freighton operator on this like Banach space, something like this, and then you can show that some of the kernel of Freighton operator is a perfect complex, which is a better way of saying that the kernel and co-kernel are not degenerate. And so this is the only place where you actually have to play a little with some. I mean, you have this infinite matrix representing G, and then you play a little bit around, but it's easy. But this is a step where you actually feel like you're doing somewhat a little bit of analysis. Okay, that is something. Questions?
So anyways, to understand this, so before you erased, actually the blackboard is fuzzy. We can't see it. We can't read the right blackboard from here. I don't know what's... but before you erased what you've written before, you had a factorization where P... okay, now it's okay. So P to P, you said that you factorize it through P, and one map is trace class.
Right.
But it seems to me that it is, you have to use that the data will not give you the map from P to P is you need some homotopy to do it. I mean, I think the data is probably that
look
the map
at the
from
references where it's executed slightly, or look at the complex geometry nodes where we do precisely the same arguments in like this liquid vector space and so on. It is some formal thing that I'm probably screwing up if I try to do it right here.
But in any case, the data probably means that the map from P to the complex is homotopic to a map that factorizes through a finitely generated free A module.
But up to homotopic, it's a factoring.
Yeah, and then you can use this finitely generated free A module to modify the presentation.
Yeah, right. So I should have said it. So this way I can modify the complex so that now in degree 0, it becomes 0, and then I can just keep going. And then
yeah, okay. Well, maybe it's the same approximate.
Yeah.
Thanks, Peter.
Did you figure out the question, by the way?
No, sorry.
Okay. Okay, see you.